Good morning, colleagues, and welcome to this paper discussion. It's paper 2, July examination, grade 12. Yes, the purpose of this discussion is to have accurate marking, but also to enhance certain understandings as well as things that you might want to go and redress with your learners, where you will pick up that there's areas where they have misconceptions. Lastly, before I jump into the paper, let me remind you that should you have queries or certain issues which are still unclear, we will have a situation where you can send your problems or your questions to your subject advisor, and they will then send it through to me and the moderator, and we will answer it on our website where you will then get more information. So keep an eye out on that. Also, the link will also still be available to look at the video again later, so it's not only a live presentation. So thank you. With that being said, let's jump into the questions, and let's go to our multiple choice questions. I will only address the ones where I think they can really be some gain for the learners or for you as a teacher. All right, question 1.1, I think that was straightforward, as well as 1.2. Now, if we go to question 1.3, I think this is important that that this is one that you might discuss again with your learners, that they should know that we are looking for one that is not. Whenever words are highlighted like this in bold or in capital letters, that is really important to be careful. We are looking for the one that is not an isomer of pentane. So it means that 3 of these are isomers of pentane, and 1 is not. So then it should be clear that the answer in this case then for 1.3 should be C. This one, if you go and you draw this condensed structure, then you will see that it's definitely not belonging to the alkanes, which then is not an isomer of pentane. So yes, while I'm talking about these condensed structures, we picked up in the March paper that learners don't understand condensed structures well, that they have problems with interpreting them, and I think it can really help you if you pay a lot of attention also in your revision later on during the year. Right, 1.4, which one of the following compounds has the highest boiling point? So to have the highest boiling point, we will actually be looking for the highest intermolecular forces between molecules. So to understand that, you have to inspect each one of these molecules, and when you inspect them, you will find that if you look at all 4 of them, they are symmetrical, and thus the forces that will act between the molecules will be London forces. Okay, and for that reason, now we are looking for the longest parent chain, and you will see the chains are of similar length. So the third step would be to go and say, right, let's look for the one with the highest molecular mass, and that will be A. Maybe make your learners aware. They sometimes see, whenever they see a haloalkane, they immediately think that the forces will be dipole-dipole forces between the molecules. That would have been true if a molecule like this was given to the learners, where you will have something like that, where it's not symmetrical. The forces that will mainly contribute here, comparing to something like that, now will be dipole-dipole. But in this case, there isn't any dipole-dipole forces because of the symmetrical nature of this molecule. Just maybe something extra that you can highlight to your learners and to enhance their understanding. All right, so that was question 1.4. If we go to question 1.5, I think that is clear that learners should know that they must be very careful when they relate intermolecular forces, and we look at things like vapor pressure. So and melting points and boiling points. They should know that the intermolecular forces is proportional to boiling points and melting points. In other words, stronger intermolecular forces will give you higher boiling points and melting points, but it's inversely proportional to vapor pressure. So stronger intermolecular forces will relate to lower vapor pressures. Now, here we are looking at branched molecules or less branched molecules. So learners should really know this work by heart, that more branched molecules, more branched, will relate to weaker intermolecular forces, to be specific, weaker London forces, and that will then relate to higher vapor pressures. Thus, A is your correct answer. Okay, so, but they can work through the rest as well. Then another very important one that learners should know is when they study your esters, is that they should know the preparation of an ester. It is a practical experiment, and you will pick this type of question up in almost every single paper. So esters as a functional group is really important for learners to know everything very well there. They should know that the methyl part of an ester's name, that was coming from my alcohol. So methyl would come from the methanol that reacted. That is one of my reactants. So that will help them to then know that the alcohol is either A or C. Now the second part is, what catalyst do we use? Yes, we use a couple of drops of concentrated sulfuric acid as catalyst, and that is the reason why 1.6, the answer will then be C, because it's methanol and sulfuric acid is my catalyst. The second part here, just for clarity, the ethanoate, that comes from my carboxylic acid that reacts with my alcohol to give me a product which we call the ester. So in this case, ethanoate, it would have, the reactant would have been ethanoic acid. This is the basic knowledge that really I think you should highlight to your learners, that they should at least be able to do this. And then of course go forward to be able to draw these structures. Right, 1.7. This is a very important question. Where learners, we pick up that learners still don't know that when there's a change in your rate, and you look at temperature specifically, that learners should know that temperature, a change in temperature will have a change in your average kinetic energy. That is very important that the learners know this. So if I increase the temperature, I'm increasing the average kinetic energy. Please make sure that whenever you relate temperature and kinetic energy of the particles, especially when we start to talk about the collision theory also, that they do know, that they show clearly, they know that not all the particles have the same kinetic energy, and that's why we will have a change in the average kinetic energy. All right, so in this case, we are looking for, there was a decrease in the reaction rate. So what is a possible correct answer here of 1.7 is that if the rate decreased, it would be because of the average kinetic energy that decreased, because that would give me a decrease in temperature as well. Okay, so that would have been a correct answer. Also very important here, for clarity purposes, if I increase temperature, I'm still going to increase the reaction rate for an endothermic reaction. If I increase the temperature, I will also increase the reaction rate of an exothermic reaction. So the reaction being endothermic or exothermic does not play any role in terms of reaction rate, but it is the average kinetic energy that plays a role here, which is clearly explained through the collision theory as well. I hope that one is quite clear. And as you will see, I'm trying to give you a little bit more information for clarity purposes. Right, then 1.8, we still pick up that learners don't know this curve, the Maxwell-Boltzmann curve, that give you a lot of information. Now in this case, we do tell the learners here that you get a graph A, and then after making some changes, after certain changes or a change, then you get your graph P. So there is the graph that was that you received after you made certain changes. Now, the changes that one would make that can influence this graph would normally be changes that will influence reaction rate, things like temperature, things like concentration, a catalyst, those factors that can influence your reaction rate. We like to show those changes. So the kind of changes that is really important here is that learners should know that the area under the graph represent the total number of reactants that can react at that moment. So that is the area under the graph. So if the area under the graph increased, then it shows you that the total number of particles that can react at that moment have increased. And for that reason, the only possible answer is that there is an increase in concentration of the HCl. So by increasing the concentration of the HCl, then I will have that the concentration is directly proportional to the number of moles that can react, and thus we will have to have a bigger area. And that's why that graph just increases like that. Why not a change in temperature? A change of temperature, we will find, will do one of two things. Let's say I increase your temperature, then you will get a lower peak and you will get a higher part there at the bottom, so that the total area under the blue graph and the total area under A can stay the same. That's why it has to change where this peak is lower and more to the right. For lower temperatures, the peak will be higher but more to the left, so that the total area can still remain the same. So I hope that this is clear, that if you get a totally higher area, then it needs to show you that you have increased the number of particles or the number of moles of particles that can react with each other. All right, so that is your Boltzmann curve. 1.9, two reactions takes place at different rates under identical conditions. Now, if you inspect these two reactions, then you will see that we've got different reactants here. So my reactance is different, and because my reactance is different, the factor here that will influence the reaction rate will be the nature of the reactants. Now, so this could have been only the correct answer. Now, let us just make sure for clarity purposes as well. In reaction 1, I have a alkane, and in reaction 2, I have ethene, alkene. So we know that less activation in energy is necessary to break the double bond of ethene, and that's why this reaction will be faster. So it's totally correct that the reaction 2 will be faster than reaction 1, where substitution has to take place. So I hope this clarifies it. Another way of explaining it would just have been to say the one is saturated and the other one not. You know that your non-saturated reactant will react faster because of less activation energy needed for effective collisions to take place, and thus for your products to form. So this is quite one of the few ways that you can actually ask a question that relates to nature of reactants. All right, and then 1.10, this is a very important graph as well, that you know that you get it often in papers, and maybe for the future also make sure that you address this with your learners for how it will look when you look at equilibrium, where there's two reactions taking place, where for equilibrium your reactants will be here and your products there. But I think it's straightforward in this case that the learner should just know, how do I use my values to calculate delta H and the activation energy of from this graph. So this is a straightforward question in my eyes, which was number B. Okay, so that being said, that is, I hope it clarifies and also give you some information to go and readdress maybe with your learners. Okay, looking at question 2, 7 organic compounds is given to the learners, and this is the way we normally will get this question. It's just a nice way of asking this question. So in 2.1.1, the first question here is, what is the general formula? Now, we find that really learners don't know this basic knowledge very well. So your basic formula for that compound will be this one here, straightforward, 1 mark or nothing, because the learner would have seen that, yes, I have haloalkane here, so that will be my basic formula that I will use there. Okay, so going to the next question, learners need to really read carefully. When we ask things like general formula, name, then we don't want a formula, or we don't want a structure, we just want the name of the homologous series. So for that sake, we just want carboxylic acids, because we can clearly see that G, in this case propanoic acid, it is a carboxylic acid. All right, so they just need to read carefully. Then 2.1.3, the condensed structure of compound B. Now there is compound B given to you, and here I would like you to add the following, and I'm just shortly going to talk about possible options here as well. Okay, first of all, let's look at our marking criteria. If everything is correct, 2 out of 2. And let's say the learner at least have the functional group correct, then indicated correctly, then we can give him 1 out of 2. So what we are looking at, the definition says that for condensed structure, that it's a shorter way of showing the molecule, where you are allowed to show certain bonds as well. So I would like us to add also this possibility here. So I'm looking for, first of all, for 1 mark out of 2, I'm looking that the O is correctly indicated, the functional group. So that any one of those are fine, that will give him his mark. And if the rest was correctly indicated, then it is fine, he will get the 2nd mark. Now, so let's say a learner wrote the following. He did this. First of all, the learner will get the mark because he did indicate the functional group correctly. He did show me it is a double bond O there, but now here you will see the learner did not condense the hydrogen and carbon. So I confirmed this with National, that you are not supposed to show bonds between carbons and hydrogens. And I think this is really something that you can help your learners with, to understand condensed structures better. The moment when they show this, they will lose the 2nd mark, which says that the whole structure must be correct. But the learner will then get 1 out of 2 because he did indicate that correctly. Another example is if I show you the following, let's say CH3, CH2, C, and the learner wrote there OH. And here he's got CH2, CH3. The learner did not get the functional group correct, so he loses that mark. And also he didn't get the complete structure correct. The whole structure is not correct. So this learner will get 0 out of 2. Okay? So because the whole structure shows everything is correct, he gets the second mark. So lastly, if a learner wrote, for the last example, CH3, and he's got that, CH2, and he's got a CO, CH2, CH3, then you can clearly see he did get the functional group correct, and the whole structure is correct. This learner will get 2 out of 2. I hope you will understand now clearly how to mark this question. And let us pay attention to condensed structures. For example, of the question now, if I can just show you this, a learner should know that if I write CH3 brackets CH2 and a 3 there, and then let's say CH3 here at the side again, that this CH2 is part of a long chain where I will have in total 5 carbons, which is then pentane. But if I write something like this, CH3, CH, and in brackets CH3, and then again my CH2, CH3. This is a methyl group that is attached to that carbon. So the learner should know that this is not part of the parent chain. This is now a methyl group. But in that case, it is part of the parent chain, because you will never have, that is not methyl that could have been branched in terms of that chain. So I hope this helps you also a little bit. You need to really work with this a little bit more, because condensed structures is in the paper. It's going to be there. We just don't know how much of it and how it will be asked. Okay, right. I hope that I haven't over-exhausted that issue, but I think the issues will get less, and let us just be accurate when we mark, so that will save time and no marks to correct later on. All right, when we go to question 2.1, I ask you, give us the IUPAC name of compound A. The IUPAC name of compound A, so this is very important that you practice haloalkanes with your learners, because our understanding here is that your halogen and your methyl groups, we treat them the same. The halogen don't get preference above methyl groups or ethyl groups, alkyl groups, when it comes to numbering. So now the first step here would be to say, all right, if I number from the left, I can clearly see my longest chain. My parent chain is consisting of 1, 2, 3, 4, 5, 6 carbon atoms. Now, if I number from the left, I will get a methyl group on the second carbon. I will get another methyl group on the second carbon, and then I will get a bromo on the 1, 2, 3, 4, 5th carbon. That will give me a total of 9 if I add it up. If I number from the right, I will have a bromo on the second, and I will have 1, 2, 3, 4, 5. I will have 2 methyls, which will give me a total of 12. Now I'm going to use that part. All right, that will be my numbering, so that I have my lowest total. Now, after knowing how to number, now I go to the alphabet and decide that I'm going to name the bromo first, because B comes before methyl in the alphabet. I know there's a dimethyl, but the D of the di is not playing a role in deciding the alphabetical order. Now, I want us to make a change here when we look at marking of this question. So I want you to just eliminate those ticks there so that it can't confuse you. We are going to follow the marking criteria. First of all, you're going to check if he identified hexane. So if there's hexane, then you will give that learner 1 mark. All right. Then you are going to look next for bromo and dimethyl. If he only wrote there methyl, he will lose the second mark. The bromo and the dimethyl has to be there. So if I see a bromo and a dimethyl, that will give me my second mark. Now, if everything else is now correct, he wrote the bromo first, he wrote the dimethyl second, he's got all his numbering and the sequence of hyphens and commas, everything correct. Now, that will give him his third mark. So this is the way we mark it. I think by putting the ticks there, it might be confusing. This is not, let's follow the marking criteria. And I hope this is quite clear on how we are going to mark this haloalkane. All right, then the next one was 2.2.2, write down the IUPAC name of compound B. Now there is my compound B, that is the ketone. I think that is quite straightforward, but let's look at the marking criteria. So we are looking for naming the chain and functional group pentanone. So if we see pentanone or we see pentan and anything -one, that is your first mark. The second mark will be on the correct numbering. So if there is a 3 in front or in the name, then that is your second mark. Again, be careful. The ticks might confuse you. So I would say I'm looking for 2 things. I'm looking for pentanone. Let it be split or written as that. That is the first mark. My second mark is now on the correct numbering, which is then 3, pentan 3-one. So that blue part will be my first mark, and the yellow part will be my second mark. Okay, so that is the way that we mark this according to our marking criteria. So just read carefully here and you actually can't go wrong. All right, next question, quite straightforward. Question 2.3.1, where we say, write down the structural formula of compound E. So learners should understand clearly that now we are asking a structural formula and all covalent bonds must be shown. Compound E is this 2,3-dimethyl-but1-ene. So there I have my structure. Let's look at the marking criteria. First mark is if he shows 2 methyl groups. Okay, if you draw the 2 methyl groups correct, and second mark is if the parent chain is correct, the parent chain having 4 carbons with the double bond on the first carbon there to form but1-ene. So I'll be looking for the methyl groups for 1 mark, and I'll be looking for the parent chain for the second mark. If the methyl groups is on the wrong carbons, of course then it's incorrect, but you can still get the mark if the parent chain was indicated correctly. All right, so I hope that helps you if I use these colors to show you exactly according to the marking criteria. Our next question was 2.3.2. 2.3.2 says, give us the structural formula of compound C, and now there's your important information. It's a tertiary alcohol. So if I go to C, I can see I got the molecular formula here, and I know this molecule will have 4 carbons, and I know that OH, because it's an alcohol, that there will be a hydroxyl group somewhere. All right, so going to the structure, there is my structure where I can see that my carbon, where the OH is bonded to 3 other carbons. That is a tertiary alcohol. So let's look at marking. If the whole structure is correct, he gets full marks out of 2 out of 2. If only the functional group is correct. So in other words, he did show you a C and a OH. He did indicate that he knew the alcohol must be a OH. Then he can get 1 out of 2. Okay, if there's more than 1 alcohol, let's say he draw 3 alcohols because he thought the tertiary has got to do with that, then he will get 0. That is what I'm saying there. More than 1 alcohol, more than 1 hydroxyl group, then he will lose that mark because he identified at least the hydroxyl group. Right? Then also, if he wrote a molecular formula, okay, any molecular formula, then you will get 0. If he did a condensed structural formula, let's say he wrote this correct, but he indicated the OH, he did not indicate that bond there between the hydrogen and the oxygen. So he wrote a condensed structural formula, he can still get 1 out of 2. If he wrote a condensed structure CH3, C, and he shows the functional group CH3, everything looks fine, but he did not draw all the covalent bonds in, he can still get 1 out of 2. All right, so I'm trying to cover all the possible answers that learners would come up with to help you to understand how much marks they can get. Be careful when you mark. Sometimes we find teachers just because of haste, it's a 0 and he could have got 1 mark there. Try to be very, very accurate so the learners get the marks that is due for them. All right, then moving on to question 2.4. Now question 2.4 is a question where we say compound D is prepared from the reaction of carboxylic acid and the alcohol in the presence of an inorganic catalyst. A water bath is used to heat the reaction mixture. And now we ask them, what characteristic, write down the characteristic of alcohols that make it necessary to use a water bath to heat the reaction mixture instead of an open flame. All right, so learners should have by a bit of interpretation, seeing why would I not use an open flame? Why will I do heating with a water bath? The answer here is the fact that an alcohol is flammable. Okay, it's flammable, so that's why we prefer to use that. No answer concerning we are doing it because of any vapor pressure. We know there will be a vapor, but that vapor is flammable, so that's the reason why we use the water. If it was not flammable, the vapor wouldn't have played a role at all. So please don't accept answers like vapor pressure. It is the characteristic that alcohols is flammable that plays a role here for using a water bath. All right. Then we ask, give the IUPAC name of the carboxylic acid that you will use to prepare D. Now, if I look at D on the question paper, it's ethyl methanoate, and like I explained earlier, the carboxylic acid will come from the methanate, will give me the methanate. So it will be methanoic acid. All right, nothing else. So the learner had to give us the IUPAC name. All right, and the IUPAC name is straightforward, methanoic acid, nothing else. No condensed structure, no structure being drawn, only the wording methanoic acid. That is the IUPAC name. Okay, right, then the next question is 2.5. In question 2.5, write down the name of the functional group of C and G. Now, if we go to C, you will see that C is this one. Let me just find my paper again. The question, right? Here is C. C was this one where I gave the molecular formula. But then later on I told him that it's a tertiary alcohol. So then it will be a hydroxyl group, will be the functional group. Nothing else. And then the other one I told them that G is propanoic acid, which they then know it is a carboxylic acid, and the group there is a carboxyl group. So I think that should not be a problem. It's 1 or 0, no other answers. Okay, so that was question 2, which was 17 marks, and we can move on to question 3. Question 3 deals with intermolecular forces. All right, before I go to this question, remember as we go through this paper, and you might still have issues of clarity, you are welcome to contact your subject advisors. They are also watching this presentation, and if they can't help you, then they will send your questions through to me, the examiner, and our moderator, and we will then put the answers on our website. All right, so going to question 3. 2 aldehydes A and B are used to investigate factors which affect boiling point, and I gave them, and they could see that A and B is 2 aldehydes. Okay, and then a learner makes a statement, and then you can see also that C is an alcohol because of the hydroxyl group there, and the same goes for D. D is a carboxylic acid because of the carboxyl group there. All right, so now we say that a learner make a statement that it is possible to draw a structural formula of a positional isomer for compound C, but not for A. A positional isomer. So positional isomer means that I can change the position of the functional group. Then it will form a positional isomer. Now, if I go to compound C and I take my hydroxyl group and I take it to the second carbon, then I will have, here it is now propan 1-ol, and if I take my hydroxyl group to the second, it will be propan 2-ol. So which shows me it's possible to draw a positional isomer for C. So that is true. Let's look at A. If the functional group, the carbonyl group, go to that carbon there, then it's no longer a ketone. Then it is, aldehyde. Then it becomes a ketone. So it is impossible in this case to just change the position of the carbonyl in this case, which is my functional group. So because I'm going to change from an aldehyde to a ketone if I make a positional change. So what this learner said, is true. Let us look at the marking then. If we look at the marking, then 1 mark on that the learner have said it's true. If the learner, if it's wrong, he said it is not true, still look at the explanation. Please still look at the explanation, and if the explanation is correct, then you can still award marks. But I think rarely we will find something like that. All right, so why is it true? It is true because now here he will have options. The learner can either say it is true because C, it will become a ketone, or they can say it cannot form a functional isomer. It can only form a functional isomer, because if it becomes a ketone, it actually was not a positional isomer. So if they refer to changing that position, you change it to a functional isomer. That is correct. Or if they are saying that it's a ketone, it's fine. So by referring to A, that is what we want. And then referring to molecule C, they will just say it stays alcohol. It stays an alcohol. Or if they say that one forms a positional isomer, then it is fine. So we are looking for that for the second mark. Explanation where they clearly show you A becomes a ketone or a functional isomer, and C stays an alcohol. Okay, so that is the way we can mark this question. All right, 3.2. I hope that clarifies that one. A compound B has a higher boiling point than compound A. Fully explain the difference. Compound B has a higher boiling point than A. So we can see that they belong to the same functional group. They are both aldehydes, and we know that our aldehydes there's 2 forces that will play a role there. It will be London forces as well as dipole forces because of the carbonyl group. So now we can see that B, the parent chain, is longer. It's 4 carbons, where in A it's only 3. So that is the factor that we will need to look at to be able to explain the higher boiling point. So this is what we are looking for in 3.2. If the learner has to refer to the chain length, so you can either say that A has a shorter chain length, or he must say B has a longer chain length. So that will give him 1 mark, one of the 3 marks, if he refers to chain length. Okay, now he needs to refer to which one then will have the stronger forces. So because of the shorter chain length, you will look for where he indicates that the intermolecular forces in A is then weaker than that in B, or you can say the intermolecular forces in B are stronger than in A. So we need that comparison between the 2 in terms of intermolecular forces. Lastly, for the 3rd mark, you will see there's a little bullet indicating the difference between the 3 marks that you are looking for. Now he has to say something about energy. So he will either say less energy is needed to overcome or to break the intermolecular forces in A, or he will say more energy is needed to break or to overcome. So that is an or situation. So the last mark, I'm looking for a referral to the energy needed, and he needs to indicate that correctly. So to summarize again, a referral to chain length, a comparison between the intermolecular forces of A and B, and saying the energy needed to overcome the intermolecular forces to indicate that correctly. So that is your 3 marks. All right. Question 3.3, the learner has got a choice out of 3 values to predict the boiling point of X. So when you look at compound C, then you see it's an alcohol, and he should know, sorry for that, he should know that the alcohol, here we will find the hydrogen bonds acting between the molecules, which is a strong bond, which is when I compare that to the other here, which is aldehydes, is stronger. So I will then, the guess would be that this 96 degrees is a correct value. It can't be lower than where there's no hydrogen bonds. So that would have been a prediction. Now we want them to refer to, and now we are specific, types of intermolecular forces. So we are going to look at if you could identify these intermolecular forces to explain the difference in boiling points between A and C. So he's going to compare this aldehyde with this alcohol, and he has to refer to intermolecular forces. It's clearly said here. So that will be definitely a mark that will be awarded. So if we look at 3.4, right, how are we going to award the 3 marks of 3.4? We are looking for the following. If he indicates that between the molecules of C, or he says between the molecules of propan-1-ol, or between the molecules of alcohols, doesn't matter what way he refrains it, he needs to indicate to us we have hydrogen bonds there. That's 1 mark. Then if he can correctly identify that there's dipole-dipole forces mainly acting between molecules of A. So that is what we are looking. The part here which says in addition to London forces induced dipole, that is just an extra, but there's no mark on that. So we don't expect that to be there. But I'm just showing it because it's possible that the learner could have said that. So up to here, the learner now have 2 marks already if he identified the 2 intermolecular forces. So that is 2 of the 3 marks. Now just be careful. Any of the following will give him the 3rd mark. If he says that the intermolecular forces in A is weaker, that is a possible answer. Or, very important, or if he says less energy is needed. So referring to comparing intermolecular forces or comparing energy needed, that is the 3rd mark. So if we do both of them, it's not 2 marks. For one of them, we will give the 3rd mark because the question states that he needs to identify the intermolecular forces. So that's where 2 of the 3 marks is going, and I hope it's quite clear that this is my or situation for the 3rd mark, is that he can correctly refer to energy or the comparison in intermolecular forces. He can do that in terms of less energy or more energy. It's clearly showed here. So that is your 3rd mark if he makes that comparison to indicate the higher boiling point of C. Okay, so that was question 3.4. Then if we go to 3.5, consider now C and D has a lower vapor pressure than C. We tell them that the following is that D has a lower vapor pressure than C. So they should now derive that means that D has got stronger intermolecular forces than C. All right, now 3.5.1, we ask them explain the difference in vapor pressure by referring to the type of intermolecular forces of the 2 molecules. All right, so 2 marks. This is how we mark it. If he indicates that both C and D between the molecules, we will find hydrogen bonds. Okay, that is the main intermolecular forces. This part of, in addition to possible London forces and dipole-dipole forces, that we are not really interested in that, but it can be there. But this is the part, if he identifies the intermolecular forces for both correctly, he gets 1 mark. If he says something like, with C it's hydrogen bonds, but between D it is dipole-dipole or London or whatever, then it's incorrect. Both have to be indicated as hydrogen bonds. All right, then the second thing is that we know that with our carbolic acids, that is my 2nd mark, there we have 2 sites for hydrogen bonding that can take place. And that's why we will have stronger intermolecular forces. So to explain this part, we were looking for those 2 things. First of all, identifying it correctly, and then stating that with your carbolic acids, 2 sites is possible where hydrogen bond can take place between 2 molecules. All right, so now we ask them, in 3.5.2 to draw this molecules, 2 of them, and to show the intermolecular forces, which will then explain what is said here in 3.5.1. Yeah, we indicated where the lower vapor pressure comes from. So there is my drawing. I don't have a problem if learners did it where this part is condensed, but the learner should know that the hydrogen bond is between that oxygen there and the H of the hydroxyl. And then there's another one possible for a carboxylic acid between the H of this hydroxyl and the oxygen there with the double bond, the carbonyl. So this is very important that the learner must be able. That's 1 mark or 0. But like I indicated, if we had problems here with drawing that part there, or he decided to use condensed structures, I'm interested in him showing me that his understanding that is where a hydrogen bond takes place. Okay, so that's 1 mark, easy to mark. I think there shouldn't be problems. All right, then we move on. This was question 3, which was 12 marks on intermolecular forces. Now we get to the question which deals with the reactions of organic compounds, and the first reaction, the learner should be able to see that that we have here a alkane that is now going to form but1-ene, which is an alkene, and that is a reaction where there's cracking. Now the first question is, write down, very important, nothing else, no structures, no condensed or structural formulas, molecular formula of compound A. Now the learner had to go and count the number of carbons here, and you will see that there is 2 molecules with C4. So just comparing my carbons, you would have picked up that there's 8 carbons in total already here. There is 10 there, so A should be having 2 carbons. Now doing the same with the hydrogens, there's 22 hydrogens on this side. There's already 16 there in that but1-ene. So in total, so there's another 6. So that's how you could come up with the molecular formula C2H6. Nothing else. 1 mark. All right. Then the conditions. Write down 2 conditions. The conditions is we need to apply heat and high pressure. High heat, high pressure. And lastly, what do we call this reaction? This type of reaction, it is, you can accept either elimination or cracking. So any one of the 2 is correct. Right, 4.2.1 is a question where I have an alkene. I have that but1-ene now that is reacting with water, and then a new product will form. First question, draw the structural formula of the major product B. So no condensed structures, no molecular formulas can be accepted. He has to draw the structure. And here he has to apply his rule to be able to get the major product. So there is my alcohol that will be forming. So let's just look at, if at least he showed a alcohol somewhere. In other words, he identified the functional group that will form correctly. He's got a OH. Even if it's on the wrong carbon, doesn't matter. Then I will give him 1 mark. And then, of course, if everything is correct, he's got his 4 carbons, he's got it on the second carbon, then that will be my major product. Then he will get 1 mark. Okay. Just be careful. If the OH is on that carbon there, then it will still be correct. Okay, then it will still be correct. If a learner wrote OH there without showing the covalent bond, then it's not, unfortunately, anymore structure that he has drawn. Then it's condensed. Then he will lose his marks because he did not draw the structure correctly. Okay, but indicating the OH, he can still get that mark. Okay, then it's 1 out of 2. All right, then 4.2, we ask here, question 4.2.2, write down the formula of the catalyst. So no names, the formula, only that will be accepted. So the catalyst is H2SO4 or H3PO4. No sulfuric acid in wording or nothing. Yeah, the question was specific, saying write down the formula. Okay, and I hope your learners don't be too lenient there now and accept if they use words, because you will not do them any favors for the way forward. Rather show to them how they actually lost marks by not being careful. 4.2.3, in 4.2.3 I ask what type of reaction is shown. 4.2.3, it is an addition or a hydration reaction, straightforward. Okay, reaction number 3, we have here some compound, it reacts with sodium hydroxide, and I see that the alcohol is forming there. Then they should know this was diluted sodium hydroxide. All right, now they ask you, write down the molecular formula of compound C. So they could derive compound C from this products that are formed here. So they should realize that it should be an organic compound with 4 carbons, and there needed to be a fluoride component, a fluor component there as well. So, and the question was the molecular formula. So this is what we want, C4H9F. So it's 2 or 0, nothing else. No other condensed structures, no other structures being drawn. It must be the formula. They need to be very accurate there. All right, then we are moving on to question 4.3. Okay, sorry, I missed one. What type of reaction is shown? Substitution or hydrolysis. Substitution or hydrolysis. Okay, so that is straightforward. Sorry, I missed this one. I did it already. 4.2.3, I got mixed up now with my numbering here. Oh, I was busy with 4.3.1, sorry. That is the molecular formula, which was C4H9F. Okay, then I ask, write down the 2 reaction conditions for this reaction to take place. And they need to know we are going to apply heat and that the sodium hydroxide must be diluted. That is 2 of the conditions. All right, so that is 4.3.2. I hope you are with me. I got mixed up a little bit between previous questions and this one. 4.3.3, what type of reaction takes place? So yes, here it will be a substitution reaction or a hydrolysis reaction. Okay, so I think that is a clear one. What kind of alcohol is shown in this reaction? Choose from primary, secondary, tertiary and give a reason. I think this will be fine. It's a primary alcohol, and the reason is the carbon atom. This is very important that they talk about the carbon atom. The carbon atom to which the OH is bonded to one other carbon atom. So they need to just be careful here when you mark that they use the correct working. We need to wording. We need to talk about that carbon atom. All right. Then question 4.4. Question 4.4 is a question where I have an alcohol that reacts now with HBr, and then I asked, write down the IUPAC name. Write down the IUPAC name of D. All right, so now the learner would have to look at it's reacting with this. So the OH will be substituted by the Br. So when it's substituted with the Br, the bromo is on the second carbon. So this is what we are looking for. We are looking for 2-bromo, 1 mark, and butane, another mark. It stays butane. It can't become butene or so on. So this 1 mark for the 2-bromo, 1 mark for the butane, and they will be fine. All right, then 4.4.2, the formula of the inorganic product E. What is it that will be forming? I've substituted the OH, it will combine with the H there, and our product will be water. Okay, 18 mark question, question 4. Okay, I'm going to stop here for 5 minutes, give you time just to stretch legs and maybe take a bathroom break. Let's stop for 5 minutes and then we will proceed to the last 2 questions. That was questions on reaction rate. Thank you. I'll see you in 5 minutes. Right, colleagues, welcome back. I hope you enjoyed your little bit of a break, concentrating through this paper. Let's go to question 5. This is the questions now that deals with reaction rate. And if we look at this question, we have a question here where we showed the apparatus being used, and it says here that the learner or the student investigate the rate of the reaction between iron and sulfuric acid. The student decide to measure the rate in this unit, cubic centimeters per second, and then we give the balanced equation. Now, the learner should look at this and see that I've got my solid, which is my iron powder. I've got my sulfuric acid, and then there's a gas, hydrogen gas, that will be forming, that will displace this water in the cylinder, measuring cylinder downwards, and I can measure the volume here. So that's just to give you a bit of background. Also important here is that learners, when they get to this kind of question, just think a little bit about what is my independent variable and what is my dependent variable. So if it clearly states here, he wants to investigate the rate of a reaction, you can know that that will be your dependent variable. And looking at this unit, cubic centimeters per second, then my independent variable will most probably be then volume. All right, so I'm just showing you that you can derive from that information already some of the variants that you will need to have. Okay, the first one was define the term reaction rate. Define the term reaction rate. So the way we want to mark this definition is as follows. And this is the way National also do it these days. Reaction rate is the change in concentration. This is what is in your terms and definitions per unit of concentration of the reactants or products per unit time. So that is for 2 marks. It's 2 or 0. Okay. However, we do accept if they refer to change in mass, change in volume per unit time. So here I've showed you your options. So if learner said reaction rate is the change in mass per unit time, it's acceptable. Or is your change in volume per unit time, it's acceptable. Or any one of these, change in number of moles per unit time. So there don't need to be concentration there. It can be any of those. But be very careful. If he says that the reaction rate is the change in concentration of the reactants or products, and he omits per unit time, 0 out of 2, unfortunately, because it's a rate that we have to define. So that per unit time is there. All right. Now I'm asking the learners the next question, where we say the student repeats this experiment at different temperatures. All right. So now I know this is actually my independent variable, because I'm choosing to do this experiment at different temperatures, and then I will find a way to measure the rate of the reaction. So yes, I'm happy. There is my independent variable, and there is my dependent variable identified. Okay, and I already started to talk here about all other variables are kept constant, things like that. So if we look at the question now, I ask here, state 3 variables that must be controlled during this investigation. So I already know that temperature is one that I'm not controlling. I'm changing the temperature, and that will influence my reaction rate. Now, a good idea here for learners is to just ask themselves, right, there's my 5 factors that will influence reaction rate. Temperature, concentration. Now, I know that temperature is not one that I'm going to keep constant for this experiment. concentration of my reactants, a catalyst, the state of division. Sometimes books talk about state of division, or they will talk about surface area, and then of course the nature of the reactants. But that one, in this case, will not be an issue because you are using the same reactants just at different temperatures in any case. So I have to look carefully for these three here: state of division, catalyst, and concentration. So if we look at the answer here, it will show you that yes, one of my variables that will influence reaction rate is concentration of the reactants. Now if I look at my reactants, it needs to be specifically the sulfuric acid, because the concentration of a solid do not change. I can't, even if I change the amount of iron solid that I'm using, I'm not changing the concentration of that iron. The reason is very simple. The concentration of iron solid will be the number of moles multiplied by the volume. So when the number of moles increase, the volume also increase. That is now of a solid. So I can't, by changing the amount of the mass of iron that I'm using, I'm not changing the concentration of the iron. But I can change the concentration of this sulfuric acid. So there is my answer. I need to keep the concentration of the sulfuric acid. I need to keep that constant. Okay, and then I want to jump to this third mark, which says state of division of the iron. Yes, I know from this list that I've shown you that state of division or surface area can play a role. So so if I look at my question here, if I'm going to use iron powder and the next time I'm going to use iron lumps, then that will create a situation where my surface area is different because of the state of division. So that is my second mark. Now, the mass of iron, you will see when you look at this list, the mass of iron is nowhere one of the factors that influences reaction rate. But now I want to show you, and just for clarity's sake, I'm doing this, that you understand where this comes from. So if I look at, here I have a certain concentration of sulfuric acid, and let's say, for example, I'm using 2 grams of iron in this reaction. All right, and I'm going to compare this reaction rate now. I know there will be H2 forming the gas, all right, from my equation. Now I'm going to change the mass of the iron solid. This is what will happen. By changing the mass, let's say I'm using now 20 grams of 20 grams of iron solid. I did not change the concentration of the iron. The concentration of the iron is constant. That's still the same. But what did I change here is the surface area that can now react with the H2SO4. This is important that you realize this. By increasing the mass, I'm increasing the surface area. And thus, the increased surface area will now influence the reaction rate. Okay, so I hope this is clear to you now. Why in this case, mass of the iron that must be kept constant is the answer. And I think we can accept thus, from my explanation here, if they say you have to keep the surface area of the Fe, the iron, if you keep that constant. So in this case, I will give 1 mark for that one there, or that will be my second mark, and then my third mark will be, which will relate to lumps or powder of Fe, which is the state of division. So that is your 3 marks that you could find there. Okay, but remember, if they say mass of iron, and for a third mark they want surface area. That can't be, because it implicates the same thing. So it's either concentration of H2SO4, and then they write surface area of Fe, then they write state of division of Fe. It's 3 out of 3. But if they write concentration of H2SO4, mass of Fe, surface area of Fe, they will get 2 out of 3 because they did not mention state of division. Those two, they are a OR situation. I hope that is clear how we can mark this question. And this part here, that I think is maybe a level 4 question that I try to build in here with this question, so that it's something that you can understand that mass can play a role, but it's because mass of a solid influences the surface area. Just be careful there. Right, I hope that clarifies that question. So if we go now to question 5.2.3, we ask, well, write down a conclusion that can be drawn from the results. All right, so there was my results. I can clearly see that as the temperature increases, then my rate of the reaction also increased. Okay, now from this data, you can see it's not directly proportional. For the 5 degrees increase there and the 5 degrees increase there, you can see it's not directly proportional. So marking this question, where you have to say, in other words, the question was 5.2.2. Oh, sorry, I skipped 5.2.2. 5.2.2 is write down an investigative question for this experiment. Now, this is very important. I think here you can now sort out all the problems your learners have with this type of question, because I really try to give you a comprehensive summary of how to address this. First of all, the learner have to identify the dependent and independent variables correctly to get a mark. And secondly, he has to ask a question, but that question can't have just a yes or a no answer. So it needs to be a question that he will have to be careful of how he addresses or how he asks the question. So we now know that our independent variable is temperature, that we have, and we know that our dependent variable is reaction rate. So he has to refer to those two things. Now, if we look at this example, and here is the correct example now for 2 marks. He asks, what is the relationship between temperature and reaction rate? So you can see my 2 variables is there, and he asked the question. So, and if I just say yes, then it doesn't answer this question. So that is totally acceptable, okay? So that is an example of a correct answer, 2 marks. All right. Now, if we go to another example, this learner asks, how will the reaction rate change when the concentration changes? Okay, sorry, that is a typing error. It should not be concentration, it is temperature. For this one, it's temperature. So you can see he identified the 2 variables, and just answering yes or no does not answer this question. So he will get full marks. Okay, now what happens if you can give a yes and a no? Then he will get 1 mark, because he did identify the 2 variables correct. So if you have something like the following, will reaction rate increase as temperature increase? You can see he did identify the 2 variables, 1 mark, but the answer is yes. The reaction rate will increase if the temperature is increased or increases. Another example, is there a relationship between reaction rate and temperature? 1 out of 2. He got the 2 variables correct, but there is a possible answer of yes or no to that question. So, colleagues, be careful when you mark this one. 1 or 2 out of 2, and of course, if the learner could not identify the variables correctly, then he won't get any marks. Then it's a 0 out of 2, because that is where the question investigative question will already be totally wrong. Okay, right, 5.2.3. Now I ask, write down a conclusion that can be drawn. So for that conclusion, I go to my results. It mentions the temperature and the reaction rate. Then he gets his 1 mark. Okay, if he got that correct relationship, that's 1 mark. Now, the second mark is for the correct relationship. We deduct 1 mark if he mentions something like directly proportional, because it's not directly proportional. So if a learner, in other words, said the reaction rate is directly proportional to the temperature, then he will get 1 mark, because he identified the 2 variables correctly, but it's not a directly proportionality. It is an increase of the one with an increase of the other, or a decrease of the one with a decrease of the other. All right? So if he just says the word proportional, in other words, he says the reaction rate is proportional to the temperature. That's correct. Okay, that implies an increase of the one will increase the other one. So that will give you 2 out of 2. I hope that helps you how to mark this question. All right. Going on to question 5.2.4 there now. Explain your conclusion by referring to the collision theory. Okay, explain your conclusion by referring to the collision theory. Okay, there, just for clarity, I want to just again show you this. What is the collision theory about? The collision theory says that in order for reactants to react, we need to have effective collisions. Okay, the collisions have to be effective. Now there is 2 conditions. There's 2 conditions that needs to be met for reaction rate. So a high reaction rate will then imply a number of effective collisions per unit time. Okay, so that is now, if I put the collision theory in terms of reaction rate, a high reaction rate will then mean that there's a high rate of effective collisions. So we will talk about effective collisions per unit time. I hope that this helped learners also now to see the collision theory in context with reaction rate. All right, now I want to go back in turn effective collisions. So here is the way we want to mark this question. We will say that, and this is very important as I indicated earlier, a higher temperature increase the average kinetic energy. That's 1 mark of the reacting particles. Okay, so what will that result in? It will result in more effective collisions per time or per unit time that will take place. That is your 2nd mark. So, of course, they still need to have also the correct orientation, but the increase in average kinetic energy will help us that there is an increase in effective collisions, and a higher rate will be achieved because there will be more effective collisions per time or per time unit as indicated here. Okay, unit time. So that is the way we need that. If he omits the word average, then he will lose that mark. Okay, and if he omits per time or per unit time, then he will lose that 2nd mark. And if he doesn't talk about effective collisions, he can't just say there's more collisions per time. He also, it must be effective collisions, because that is exactly what your collision theory states. All right, and it will also help you to answer the next question, which is to mark question 5.2.5. It says here now, explain by using the collision theory. So I have to refer to the collision theory, how the rate of the reaction, I have to refer to the rate of the reaction, changes if lumps of iron are used instead of iron powder. All right, so let's see when we look at this question here. Okay, so if I use lumps, then if I go to my summary here, you can see I'm not going to affect the kinetic energy part at all, but lumps will affect the orientation part of the collision theory. Okay, so now you will understand maybe why we give a mark on certain things. Right, so if the learner's right, less particles will collide per time unit. Why? Because less particles will have the correct orientation. Can you see, by referring to orientation, I have now addressed the collision theory. Now I have to relate that according to the question to reaction rate. So the learner have to say now that because there's less particles with the correct orientation if I use lumps, then less effective collisions per unit time will take place. That's my second mark. And because of that, the rate of the reaction will be less. So that's my third mark. Now I've clearly explained the using of lumps, how it will influence the reaction rate. So there you will understand now the 3 marks. So look for those there. Again, if it omits effective collisions or per unit time, unfortunately loses that mark. If he states that the rate of the reaction will be less with lumps, fine. If he does the opposite, where he refers to powder, then he will say in the case of powder, more particles will have the correct orientation, more effective collisions per time unit, and the rate of the reaction will be more. So just be careful, see maybe, but the question referred to lumps, so it should be this, but let's give them the benefit. If he clearly says that he's answering the powder, that where he put the opposite of all of this, I think it is fine. Okay, 5.2.6. Now I introduce a catalyst. Okay, a catalyst is introduced to this reaction, and I ask here, how will the rate of the reaction change if I use a catalyst? All right, now the catalyst, of course, it's straightforward, will increase the reaction rate, 1 mark. And now I ask, redraw this curve, following the Maxwell-Boltzmann curve in your answer book for the reaction taking place at 15 degrees. Then clearly show how it will differ when a catalyst is used. All right, so here is my marking criteria. The learner had to reproduce the graph, and the X and the Y is quite important here. That's why it was provided there. So he needs to indicate that X and Y again. Now here is our marking criteria. Okay, if he shows that the peak is still Y, then we are happy with that part, it's 1 mark. But now for the second mark, using a catalyst, he needs to show that this line that represents the activation energy, that it moved to the left. Okay, so if he showed with an arrow that it moved away from X towards the left, it is fine. But just be careful here. If that X is still there underneath that line, then he's going to lose. He's going to forfeit the second mark. I think it's quite clear that this line has to move to lower kinetic energy. All right, so that is the role that a catalyst would play there. I hope this is clear. All right, then I asked him again, redraw this Maxwell curve and show now the change on the curve if the temperature increased from 15 degrees to 20 degrees. Remember to label the graph so that one can see the differences. All right, so here we are looking for the following, and this is our marking criteria. Again, he has redrawn the graph, and if I can just correct this here, there's a little mistake here. The X should be there with the activation energy, and the Y should be there. So please just correct this. I will also post on the on the website this graph again where I have corrected that. So that y should not be there. So we have got our two ones. And now, in terms of the question, it clearly has to show us the following. We want to see a lower peak. So you can see there that peak is now lower than y. That was indicated on the initial one. Okay, so the new peak needs to be lower, right? And then it also needs to show that that new peak of the graph is to the right of the original one. So it shows that the peak is now at a higher kinetic energy. All right, that is your second mark. And then third mark is if it shows here that if you can derive this, that this area is now bigger than what the previous area was. That was the previous area under the original graph. Clearly you can see that this area is now, the new area is now the blue and the green. So that is what the change in temperature will create, is that this area becomes bigger. So that implicates that more particles have got kinetic energy now higher than the activation energy. So you are looking for a peak lower than y, you are looking for that peak moving to the right of the original peak, and you are also looking for more particles with sufficient kinetic energy. So that area needs to be bigger. Okay, so look for that for the 3 marks. I hope that is clear. And I will correct this drawing and just put it on the website as well. Okay. So the next question, that is question 5, 20 marks. Let's move to question 6. In question 6, our last question, it says here the following combustion reaction takes place with ethene gas reacts with excess of oxygen gas. So that is important. My oxygen is in excess. All right, so it means that my ethane will be, that this reaction at some stage will be completed, and because I've depleted the ethane. All right, now experiment 1 is represented by graph A, and experiment B is represented by 2 is represented by graph B. And what we are looking at is the volume of CO2 that have formed. So we measured the volume that have formed and we've plotted that graph. So it's volume against time. All right, question 1. Calculate the average rate of the reaction in cubic centimeters from T40 to T equals to 120. So, and that is now for experiment 2. So if I go to experiment 2, which is graph B, then I'm looking at 120 and I have those values there, and I go to 40 and I have those values there. So I want to get the average reaction rate between those 2 times. All right, so I think there should not be a lot of problems marking this question. I must just find my memorandum here. Here it is. Sorry for that, I found it. Okay, to calculate the reaction rate, it is 120 minus 40, that's the 2 times, and then I will have the correct cubic centimeter volumes. Right, 1 mark on the formula, and then 1 mark on the correct substitution, 1 mark on the answer. So that gives you your 4 marks. Now, if a learner wrote down here, gradient equals to, or average gradient, should even be more correct, is equal to this, it's fine, but then at the end, he has to indicate that that answer is the reaction rate, because we asked in the question, if you look at the question was not to calculate the average gradient between those times. The question was calculate the reaction, the average rate of the reaction. So then he has to indicate somewhere that he knows that the average gradient will also be the reaction rate. I hope that is quite clear to you, that if he wrote here not reaction rate equals to this, then he has to indicate it later to get that first mark on the formula. Okay, but substitution at the top, substitution at the bottom, and answer, no problem, 4 marks. Okay, now 6.2, at question 6.2, we ask, how does the number of moles C2H6 that reacted in experiment compares with the number of moles that have reacted in experiment 2? Choose from more, less, or the same and give a reason. I think this is quite clear. It will be the same, and the reason was the same volume formed for A and for B. So if I look at my graph, you can see the same volume of 60 cubic centimeters formed in total for both, and that being the limiting reagent, it's clear then. You can clearly see that volume have already formed at 60 seconds for experiment 1, and it took much longer for that volume to form for experiment 2, showing you the rate of the reactions is however different. Alright, question 6.3. Which graph, A or B, represent the reaction with the highest reaction rate? Okay, I think you all will be happy that it will be A, and the reason being that the maximum volume has formed in a lot less time, so you could have derived that from the graph. Okay, then I ask, at what time was the reaction completed for graph A? Okay, there was no more CO2 being formed after 60 seconds. So that is your answer for 1 mark, 60 seconds. All right, now 6.5, graph A was the result of lowering the activation energy. And how can this be achieved? So I got this faster reaction than experiment 2 by lowering the activation energy. There's only one thing that can lower the activation energy, and that's the use of a catalyst. So that is how this was obtained. 6.5 I think should be quite clear. And then if we go to the last part, which is question 6.6, redraw now the following graphs in your book and complete them for experiment 1. Okay, now for experiment 1, the learner have to see I'm looking at the limiting reactant. It's the ethane, and what will happen to the number of moles of ethane per unit time? Okay, so there's my graph. At the beginning I will have a high number of moles, and as it reacts, that number of moles will go less and less until it reaches 0 when the reaction is completed. And that was for experiment 1, it was after 60 seconds. And we did not even expect them to put in values here, but we could have added in there something like that, and you can maybe show that to your learners. Okay, so how will you get marks? The shape of the graph, not being a straight line, is the 1 mark, and ending on the time axis. Ending there will be your 2nd mark. I think that is quite clear. And then the next one was, how will the reaction rate differ, or how will this graph look for the reaction rate against time? We know at the beginning the concentration of the reactants is very high, and therefore the reaction rate will be very high, and that is why you will get the very same curve also for reaction rate against time. So again, the rate is completed here after 60 seconds. There's no more reaction taking place. The shape and ending on the time axis is your 2nd mark. Quite easy. I just, for clarity purposes, wants to show what would have happened to the number of moles of the reactant that is in excess. All right, so we will get the same. The number of moles will decrease, but it will never end on the time axis because it is the excess reactant. So there will always be a number of moles left here after 60 seconds when the reaction was completed. Maybe something just as an extra for you to show your learners how these graphs will differ. And when it's in an open system, they really need to be careful. Are we drawing here the limiting reactant, or are we drawing the yellow line, the reactant that is in excess? I hope that is clear and that you are happy with the paper that your learner have written. And from my side, in conclusion, press on with curriculum coverage. I know you've got a huge task this term, and so that we have time for drilling and revision and preparing them for the September exams. Good luck, colleagues. We are here to support you, and I hope that this memo discussion also served that purpose. Good day to you.